Welcome back. So we were talking about differential privacy, basically how sensitive a learning algorithm is when we make a slight change in the training data, and we talk about epsilon delta dp. Basically, that means that some notion of privacy loss is bounded by epsilon with probability at least 1 minus delta. And we also talk about randomized response as a very simple example of a mechanism that satisfies differential privacy. And we talk about how we can, so basically pose this question, how can we generalize the idea of injecting noise to make sure when our outcomes are not necessarily binary, we can still satisfy differential privacy. To do that, again, our main idea remains the same. We're going to leverage noise injection. In particular, in randomized response, where the responses are binary, 0 or 1, what we are doing, we are adding the right amount of noise to make sure that we strike the best balance, let's say, between privacy and performance to our data. And the type of the noise that we add basically depends on the type of the response that we are providing. In that case, the responses were binary, so the type of the noise that we are adding to our responses were also binary. In particular, we were adding the right amount of Bernoulli noise to our data. And the higher the epsilon, the more noise we add. Therefore, the more we are ensuring privacy. The smaller epsilon was, the lower the privacy loss, but also the lower the accuracy. Okay. So we're going to therefore leverage the same exact idea for broad cases. In particular, to guarantee differential privacy, we can add noise, but with different kinds to the input. Okay. So more generally, the outcomes are basically real valued. So we're going to add real valued noise to our outcomes. Okay. So in particular, there are two mechanisms here, two noise mechanisms that we typically resort to, especially when it comes to the context of leveraging differential privacy to optimize different models. And those are Laplace mechanism and Gaussian mechanism. As the name suggests, we are adding Laplace noise in one case to our outcome. In another case, we are adding the Gaussian noise to our outcome. Okay? So let's talk about them a little bit. So let's say that we have some function of our original training data. Okay? So basically, the function takes some data set and returns a vector in RD. Again, the way that I think is intuitive to think about this is, let's say that our function is maybe the parameters of a different model. We have some data, okay? We form an empirical, let's say, risk minimization problem. We form a training problem. We use our training algorithm to find some optimal or suboptimal solution. We call that, let's say, W hat. Okay? So I can think of H to be that W hat, basically. That depends on the data I've used in training, and it's also d-dimensional, because, for instance, I have, like, I don't know, 100 million learner parameters. Okay? So H is something that takes the training data and is vector valued. So the outcome is going to be some vector in RD. Then the Laplace mechanism says that all you need to do is to get a differential private mechanism is to define this mechanism. It's a randomized mechanism again. It takes the outcome of H, and then it adds a vector of all noise to it, where each coordinate, EI, is basically a random variable that is distributed according to the Laplace distribution. Okay? And the coordinates are also independent. Okay? So what is the Laplace distribution? It is very similar to the Gaussian distribution. It has, let's say, a mean parameter, mu, and something that resembles a standard deviation, b. Okay? So in particular, the probability density is proportional to the exponential of minus the absolute value of E minus mu divided by b. Okay? Again, mu is nothing but the mean, and B is related to the standard deviation. In particular, the variance is going to be 2b squared. Okay, so that's the Laplace mechanism. Gaussian mechanism is almost identical, except instead of adding a Laplace noise, we are adding a Gaussian noise. Okay, again, we have a function, takes some training data, and then returns a value in RD. Okay, Gaussian mechanism, we define a randomized mechanism that takes the original outcomes and then perturb that with some noise. In this case, the noise are, again, distributed according to the Gaussian distribution with mean 0 and variance sigma square. Okay. Again, each coordinate is going to be also independent from each other. Just to refresh your memory, the probability density of a Gaussian distribution is proportional to the exponential of minus absolute value of E minus mu square divided by 2 sigma square. But again, the mean is mu, the variance is going to be sigma square. All right. So therefore, for more general cases, when we have, again, real valued quantities that we want to make sure that they satisfy differential privacy, we incorporate continuous noise, let's say Laplace mechanism or Gaussian mechanism. Okay. But one question that arises here is, again, the strength of noise. How strong the Laplace noise or the Gaussian noise have to be to make sure that I satisfy differential privacy. In the random response case, basically that was a question about epsilon, okay? Or so the epsilon that we are using in to generate a randomized response, okay? And we argue that, for instance, if epsilon is small, again, we satisfy differential privacy, okay? So therefore here, the similar question is, how large or how small should B and sigma be in order to make sure that when I leverage Gaussian mechanism or Laplace mechanism, I get something that satisfies differential privacy. Okay. Now we're going to do this some simple calculation for the case of Laplace mechanism first, and then we also we are going to state the result for the Gaussian case because that calculation is in some sense more involved. Okay, so let's consider the Laplace mechanisms and let's see how that leads to satisfying the definition of differential privacy. Okay, so in our case, the mechanism, again, is just some vector that takes the original outcome, which was also a vector, and adds another vector to it, where each coordinate is, let's say, an independent random variable distributed according to the Laplace distribution. Okay, so each coordinate, therefore, is distributed according to the Laplace distribution, where the mean is basically the original outcome. So I use hi to refer to the ith coordinate, and the variance is b squared or 2b squared. In other words, the standard deviation is something like b. Okay. So therefore, if we are interested in studying differential privacy, we have to again look at this ratio. The probability of my outcome when my original data is d over the probability of the outcome when I make a slight change in the training data. In particular, I change one data point from, let's say, x1 to x1 prime. Okay. In this case, we have to study this, and this is exactly what we did for the randomized response case. Okay. Here, this ratio is actually quite simple because we are again talking about the ratio of two Laplace distributions with different means. Basically, that's what we are doing, okay? And it turns out that with very simple algebra, and also recalling the definition of L1 norm, which basically says that for a vector, L1 norm is nothing but the sum of the absolute value of all coordinates. We can bound this ratio in a very elegant way. So the ratio will be bounded by the exponential of some difference over b. Which difference? The difference is basically the L1 norm of h when I use d as my training data minus h when I use d prime, the neighboring data set, as my training data. So if I want to satisfy differential privacy, therefore, I have to let this to be, let's say, some e to the epsilon, which basically means that I have to set the variance to be proportional to this difference divided by epsilon. So what this is saying is that if you want to get a again, very strong differential privacy guarantee, epsilon has to be very small. So in this case, epsilon appears in the denominator of B, so B has to be very large. Okay. On the other hand, when this difference is large, okay, B also has to be large. Again, this difference is some notion of sensitivity, because what it's saying is it is capturing how much the output is going to change when I make a slight change in the training data. So in some sense, it is talking about the sensitivity of my original learning algorithm H, or my original model, learning model H. Okay? So therefore, for Laplace mechanism, we can get epsilon 0 differential privacy, or pure DP, if we set the standard deviation to be proportional to this notion of sensitivity divided by epsilon. A similar calculation, which is slightly more involved, shows that for Gaussian mechanism, you have to set the standard deviation to be proportional to again some notion of sensitivity, some difference, but here captured by L2 norm as opposed to L1 norm, divided by epsilon times log of 1 over delta. So this basically means that with Gaussian mechanism, we can get epsilon delta dp, we cannot get pure dp, but with Laplace mechanism, we can actually get pure differential privacy. Okay. So as I mentioned, therefore, these two differences that appear in the numerator of the standard deviation for the Laplace mechanism and also for the Gaussian mechanism here, they are notions of sensitivity. Okay, they capture how sensitive our learning procedure is with respect to small changes that we are making in the training data. The more sensitive they are, the more noise we have to integrate to compensate for that and make sure that the privacy and make sure that the differential privacy is satisfied. Okay, so therefore we want, in some sense, we want algorithms or models that are less sensitive. Okay, the less sensitive they are, the higher the chance of satisfying differential privacy. Okay, all right. So therefore, this is a good segue to talk about implications for deep learning optimization. Okay, so how can we integrate noise injection to make sure that when we train a specific deep learning model, the outcome is private. In particular, we want to find ways that we can integrate in our learning problem, integrate in our algorithms to make sure that the final model satisfies this strong notion of privacy, namely differential privacy. And this is something we're going to talk about in the next video. I'll see you there.